All right, the topic, part B, binary search and a selection problem. All right. This binary search topic actually well known, so most of us know about this binary search. But here, I want to go through the whole process using problem-solving thinking. So we want to understand the whole question using our problem-solving thinking strategies and methods. All right. Two topics. The second topic, selection problem. So we want to give a whole general description on the selection problem. After we solve several special selection problems, for example, find the median, finding the median, so one special important selection problem. But we also want to look at how to solve all the selection problems. All right, B.1, binary search. We use the elimination method to understand this binary search. Remote control. Yeah, all right. Let's look at the question first. Search an ordered array. This time, our data given an ordered array this time. In ascending order. Okay. Yeah. Our question. Also, a search key V. Yeah. So then, the question: how to find an index I such that V equals A of I? Yeah. So we want to get the most efficient method here. Yeah. All right. So in this question, you can see the data given has a special structure. So we want to take advantage of it. So what's the special structure of our data? Ordered array. So we do not need to do sorting, right? Yeah. We know sorting is pretty expensive. Yeah. Here, we do not need to do any work to organize our data. So our data is well organized with a good structure. So we should take advantage of it. But the question is, how do we take advantage of the given structure of our data? Yeah. So the idea, let's think about some special strategy here. Yeah. Reduce the problem size by the ordered data property. Yeah. So that's a pretty generous strategy. Reduce the problem size. Okay. More specifically, by the elimination method. Yeah, because even if you have this high-level strategy, yeah, we want to reduce the problem size. But the question, how do you do it? How do you make it happen? Right? Yeah. Elimination method. Then, how do you apply elimination method? We take advantage of the structure of the given data to help us achieve that objective. All right, yeah, okay, yeah. Let's look at the details. Yeah. All right. So we need to find a, simple way to help us take advantage of this ordered data property. All right, yeah. So let's take a closer view on our data. Yeah. Ascending order, yeah. So here, let's draw a simple diagram. Our data, the elements in the given array in ascending order here. All right. Then, when we start our first comparison, we have many options, right? Yeah. So the given key V. Yeah. Yeah. So here, we assume the given key value V, the given key value V should be matched by one of the elements in a given array. So here, as we, the general data processing setup before, so we can assume all the elements are distinct, right? Because, at this point, we have no problem on this simple step. Then, here, another assumption we can assume, V should be equal to one of the elements in the value of the elements in the given array. That's reasonable. Because otherwise, it's possible V may not appear in the given array. That's possible, but we consider that case later, right? So here, let's assume V must be equal to one of the value of the elements in a given array. So in this way, we can do the main processing work. Let's do our first comparison. The first comparison is the most important, because we need to find the right direction to go. We don't want to go random direction. Question, Lauren?
Why does it go up to the -1 instead of h?
Because, okay. All right. Because the subscripts start from 0. And we want to use n to represent the data size, the total data size, number of elements, n. Otherwise, so if you use n, subscript n, then the data size is n plus 1. It's not a big deal. Just people, also matching our programming. Programming, when you declare, right, the size of array, so you need to use, so here, I think, let me clarify this question. Although simple, but we want to get a clear understanding. When you declare a size, let's say 100, so you want to create an array with 100 elements, you declare a pair of brackets 100, right? That's the size. But when you go through all the elements in a for loop, your counting variable I or j goes through from 0 to 99, right? Because you can never use 100 as the index value. So here, the same thing. We declare this array with the size n, but when we go through all the elements, we have to start from 0 and n minus 1. That's our natural way in programming, matching our programming way, right? It's not a math class. In math class, people may like to start from subscript 1 through, x1, x2, right? So that's the way math people like to start. Our computer science people, we like to start from 0. So that's one important difference between math people and CS people. All right. Now, next, we have so many different ways to start our first comparison. We have freedom to choose, right? The first comparison, we want to compare V with one of the n elements. Now the question, which one? Which element, if we select our first comparison between V and that element, it will give us the best possible result? That's the main question we want to answer. When we have a lot of freedom to choose, we want to choose the one with the best overall result. That question, the most important question for binary search. All right, yeah. Think about that. So we need to try to understand more details after one comparison. Yeah. How do you make your decision on your choices? Which one is better, which one is worse, right? So you need to understand that question. Yeah. So for which aspect you can apply your optimal decision. Yeah. So you need to target one particular aspect here. Okay, all right. So what is our understanding for a better choice versus a worse choice? Yeah. So let's think in this way. Yeah. We want to consider two choices. One is better than the other. We want to see what's the difference between them. Yeah. So that question. Here, we want to look at the elimination aspect. Yeah. Because here we want to use this specific elimination special view to make our better choice. Elimination. Yeah. All right. Because, think about it. After the first comparison, part of the array, part of your data in the array can be eliminated, right? Yeah. So here, let's make connection. Connect our comparison with the elimination. Yeah. So after the first comparison, we can eliminate part of the array. Yeah. Then, the more elements, if we can eliminate more elements, then can we say, yeah, if one particular comparison results in elimination with more elements, can we say that's our better choice? Yeah, because choice A, choice B. Choice A results in more element elimination. Choice B results in fewer element elimination. So then we can say choice A is better. Yeah, because we want to do more elimination, then we can reduce the problem size larger, right? Yeah. So that's our criteria. That's the criteria we want to use to make our decision. Yeah. But nobody tells you that, right? Yeah. So this hidden criteria, because nobody would give you this kind of criteria used in problem solving. So you need to use your analysis work. Yeah. You need to do a lot of analysis work in your mind to figure out some suitable criteria. Yeah. All right. So here, now let's want to get into more details. All right. Let's look at when we compare V with the last element. Yeah, we want to do some experiments. Yeah. To get more detail, we need to do experiments. Yeah, because if we just do general discussion, too abstract, right? Yeah, too abstract, general discussion. So we want to do some concrete work, yeah, working on some specific elements to get more details. Yeah. All right, so the first experiment, let's compare V with the last element. So there are two possibilities, right? Two cases. Yeah. Yeah. So this case, yeah, when we go to the right branch, yeah, comparison, so it's a, two branches. Yeah. The right branch, that's the best case, right? So that means V greater than the last element. Then we can make conclusion already, right? So after one comparison, we can already make our conclusion. Yeah. So the other case, we need to go to the left branch. Yeah. So we can imagine there is a tree. Okay? Yeah. This node, there is a, when we do comparison corresponding to this node, we have two branches now. All right. Yeah. So this branch, the other cases. Now you can see, obviously, if you use the elimination point of view to understand this step, what conclusion can you make using the elimination point of view? Two cases. All right. For the best case, you did the minimum elimination, right? Yeah. You did the minimum elimination. For other cases altogether, because there are many different cases included in the left branch case. Okay? For this case, that means V less than A sub n minus 1. In this case, you have the minimum, best case, you have the maximum elimination, right? Yeah. So maybe maximum elimination. But for the left branch, you get a minimum elimination, right? You eliminate fewest possible number of elements from the array. Yeah? All right. Yeah. So that's the pretty obvious in this experiment. So the next question is, here, between these two cases, best case, one of the two cases, all other cases together, another case we consider. We want to compare. Right? Next question is, which of the two cases we should target in our current problem solving? Yeah. There are two cases. Yeah. So we need to put our main focus in one of the two cases. Here my question is, which of the two cases we want to make it our main focus in our problem solving? Think about that. Yeah. Yeah. Which of the two is our main target? Best case, worst. Yeah, we can treat this as a worst case. How about that? Everything together, one big case, we can call it a worst case, right? So, do you want to target the worst case or do you want to target the best case?
Worst case.
Yes, worst case. Not best case. Okay? Not best case. Yeah. Here, the reason is very obvious. So let me explain this step, the rationale behind this step. Yeah, because when I did the grading, I noticed many students, so let's say the last question in the homework assignment number 1. Yeah, so that's a relatively hard question. But many students give me the best case. Yeah. And we want to find the answer for the worst case. Yeah. So the reason, when I do not say anything, some of the questions I say, we need to solve the problem for the worst case. But for some other problems, I do not say it. I just ask you to solve the whole problem. So the default for the whole problem solving, you need to find a solution for the worst case, not the best case. Even if I do not mention that. I do not say for the worst case explicitly, you need to target the worst case. Yeah. The reason is very obvious. If you can find a solution for the worst case, then you will not do worse than that for all the other cases, right? Yeah, because you already target the worst case. It can never be worse than the worst case, right? Yeah. So for other cases, you can only do better, not worse. Yeah. Yeah. That means I believe you can solve the whole problem no worse than your worst case solution number. Yeah. All right? But if you just solve best case or non-worst case, some solution may not be the best case, but non-worst case, then I do not believe you can solve the whole problem with that number of comparisons. Yeah, because there is some worst case. I don't think you can solve. I don't believe you can solve. All right? Yeah? So here the logic is that simple. So here, in order to convince people we can solve the whole problem, we have to target the worst case. Yeah. So that means this part. Yeah? Very obvious. So we move forward one step, then next step, step by step in our problem solving. The next step is, so here, when you compare the size of best case, here, the number of elements in your data, there is a size, right? Yeah. So for the best case, the size is 1. The worst case, the size is n minus 1, right? Look at the big size difference. 1 versus n minus 1. The difference is very big. Okay? Yeah. Yeah. So that's the extreme case. Yeah. Think about it. So we have two cases. One better one, one worse one. Now, because when we do the comparison with the last element, that's just one of the possibilities, right? Can we consider we compare V with one of the elements in the middle somewhere, right? Yeah. So V with one of the elements in the middle. We have two cases, right? Two possible cases. One slightly better, the other slightly worse, right? Yeah. But can we say we want to focus on the worst one? If we have two different cases, we want to work on the worst one, right? Yeah. Then, all right. What is, so based on this understanding, we have a better one, worse one, all right, the two different sizes. Then, based on this observation, so which option is the best for our first comparison? Yeah, we have so many options. In all these options, can you find one with the best final result? Yeah, best final result. Yeah, which option is the best? Yeah, among so many options. Yeah. Two sizes. You look at the sizes of two subarrays. Yeah, split somewhere. So when you make your first comparison, basically you split your array into two subarrays, right? Yeah. Then you look at the sizes of these two subarrays. Yeah. One slightly larger, the other slightly smaller. Okay? All right. So, but you want to target the larger subarray. Okay? But when you target the larger subarray, you want to make the size of the larger subarray as small as possible, right? Yeah. 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 Because the size, if it's too large, that means in your second step, you need to do more work, right? If you make the size of the larger subarray as small as possible in your next round comparison, you can do less work, right? Yeah. So, based on this understanding, So which option is the best? Yeah. So the larger subarray, you make it as small as possible. That's the best option. Okay? Yeah. Is it the case the element should be in the middle of the position? Yeah. Right at the middle, the midpoint. Yeah, let's say the element we choose for our first comparison should be located at a midpoint, yeah, or near the midpoint, as close as possible. Because that midpoint, the split you get, basically, the two sizes of the subarray is almost the same, right? Yeah? Larger ones, smaller one, yeah? Pretty much the same size. Okay? In that way, the larger one, yeah, you know, no matter which one, right? No matter which one, it will be the smallest possible size for the next round. Yeah. So that's our understanding. Okay? Yeah. So here, I also want to use this well-known Murphy's law to view. Yeah. So the same question, but we want to understand it from different angles. So one special angle related to this Murphy's law, yeah, we to help us understand. Murphy's law means anything that can go wrong will go wrong. Okay, yeah, just the meaning. Yeah, all right. So here, how do we apply the Murphy's law in this step? Elimination step. Anything that can go wrong. So we need to understand the meaning of go wrong here. The go wrong in our context here, go wrong means yeah, right, yeah, very good. Yeah. So the element, yeah. V appears in the worst case. Go wrong. So go wrong corresponds to worst case. Okay? The worst, then it's wrong direction, right? Yeah. Because worst case results in more work. Okay? More work versus less work. So the more work direction, can we treat it as a, yeah. So here, the understanding this is the wrong thing, we need to, yeah. So here, yeah. So did you say, yeah. All right, yeah. So here, yeah, because, yeah. So here there is an interesting view here, is the people call it adversary argument. Here. So related to understanding of this Murphy's law, it's better we use another interesting method in problem solving. That's called adversary argument. So we imagine there is some smart adversary. Yeah. So this adversary must be very smart. Okay. So we use this adversary to help us fight against the worst case. Because here, we target the worst case, right? Yeah. always say we are only interested in the worst case. For non-worst case, we're not interested. All right? Yeah. But the question is, to find the worst case is not easy, right? When you work on a given computing problem, to find the worst case, it may not be easy, right? Yeah. Yeah. So in general, it's not very easy to find the worst case. All right. Now, we create this adversary figure in our mind. So this adversary plays a role to produce worst case for us. Okay? Yeah, because this adversary is very smart. Okay? Yeah. So it can find, when there are several options, this adversary will pick the worst case for us. Yeah. So its goal, the adversary wants to make our lives harder, not easier. Yeah. Make our lives harder, not easier. Okay, all right. Yeah. So here, let's imagine that adversary role. Yeah. All right. When we have many options, so the adversary will always produce the worst case for us to fight, to slow down our algorithm, right? Yeah, that's the role of a typical adversary. All right, so now, anything that can go wrong, yeah. So this going wrong, so we understand it's the worst case. That's the case that adversary will produce for us. Okay, so the adversary will offer us this worst case to fight against it. Okay, all right. So this statement tells us we should always deal with the worst case. How about that? So here I want to use a different interpretation. Yeah, in different situations, people may use different interpretations, right? Here, in our current situation, we use the interpretation is the adversary always produces the worst case for us. For all the steps, from beginning to end. So in all the steps in our problem solving, our adversary always produces the worst case, all the way down from beginning to end. Yeah. So anything that can go wrong, so that wrong, so corresponds to the worst case. Okay. Will go wrong, so we always work on the worst case. That's our interpretation. Okay. Using the adversary argument. Yeah, because if we use different argument, you may question the logic, right? Yeah, people may, because when people use different interpretations, they may question the logic. Yeah, so the logic looks not quite right, right? Yeah, because there are some possibilities not going wrong, right? Yeah, so people question the logic. Yeah, so here, I don't want you to question the logic. So I want to use this adversary argument to make the logic sounds right. Yeah, make the logic sound right. Yeah. All right. So that's our interpretation in this situation. Yeah. All right. So now let's target the worst case. But for the worst case, when we have two options, the adversary always picks the worst one. So what is our strategy against the adversary? Yeah, we need to fight against the adversary. Yeah, so that's another interesting understanding in typical problem solving when you use the adversary argument. Yeah. All right, so we agree. So our smart adversary always pick the worst subcase for us to solve. Yeah. But we want to design some effective strategy for our adversary. to reduce the impact of our adversary, to reduce it. Yeah. Okay? Yeah. So our strategy is, yeah, we can apply our freedom to choose. Yeah, the freedom. So our resource is our freedom. When we use our resource, the freedom resource, so we want to make our adversary reduce the impact of the decision of that adversary. Okay? All right. So the freedom is, we use that. Yeah? So two subcases, one larger subarray, one smaller adversary. So our strategy, we want to make the sizes of two subarrays as equal as possible. How about that? Yeah. Yeah. So when we make our selection, the two sizes of two subarrays, how about we make the sizes of two subarrays as equal as possible? This is the best strategy for us to fight against our adversary. Why? Because when the adversary pick the larger one, either one has similar size, right? Yeah. Yeah. So in that way, the adversary cannot do two, cannot make our option much worse, right? Yeah, how about this understanding? Yeah? So two almost equal cases. Yeah, almost equal. Yeah. So the adversary can pick either one, but either one won't make much difference, right? Yeah. So that's our best strategy to fight against the adversary. Yeah, try to understand. Yeah. Yeah, because this kind of logic thinking, yeah, very abstract. Yeah, but if you get the idea, yeah, it helps in our general problem solving. Yeah. So when you target the worst case, sometimes you can use this adversary argument to help you, guide you to fight against the worst case. Yeah. All right. Yeah. So here we spend a lot of time trying to understand well. Yeah, because it's not very easy to understand. After we complete. Yeah. So. Yeah. All right. Yeah. Yeah. So in the middle. So now we know. So for that case, the adversary will not make our any choice very bad. No. All right. Pretty much the same. So here, yeah. So the first comparison, every time when we select one of the elements to do comparison, we should select the median element. Okay. All right. Yeah. Yeah. So the strategy, yeah, here, another bad. So here, another. Yeah, so here, yeah, because another interesting view is this strategy. So here I want to call the balancing principle. Yeah, because when we split the data, which is the best way to split data, right? Yeah, here. Our current question. The best way to split the data, divide and conquer, right? Remember? We need to divide our data into two subarrays. Divide and conquer in this situation. Yeah. The best division is, we call the balanced division. Balanced division would result in the best overall result for the worst case. Yeah. Our first experiment, it's unbalanced, right? Yeah. The sizes of two subarrays, the difference is too big. Yeah. 1 versus n minus 1, the difference is too big. So it's the most unbalanced division. Yeah. Yeah. So we don't want to consider this case. So we want to make the most balanced decision when we have freedom to choose how to split the data. Yeah. So that's another useful view of this question. Yeah. So this balancing principle. Okay? Yeah. Later, yeah, later in other divide and conquer problems, we can use this understanding. Yeah. All right. Next. Yeah. So let me go a little faster. Yeah, because this step relatively hard, so I spent a lot of time. Yeah. The next step, B.2, efficiency analysis of binary system. This time, we need to look at the efficiency. Yeah. So here, we pass that divide and conquer step. Now we want to consider how efficient if we apply the strategy. Yeah. So what strategy? We always compare the given key with the median of the current array. That's the current strategy, median of the current array. Yeah. All right. Yeah. Now we want to do the, do some specific math work. Yeah. All right. So number of comparisons for the worst case. We want to see how many comparisons do we need for the worst case. Yeah. All right. Here I use one line segment to represent the size of the current array. Or the given data, size of the given data, this line segment. All right, so the first comparison, we compare the given key to the element with location right in the middle. Yeah, so here, we do estimate. We use this diagram to do the estimate. Okay, yeah. So small error, it's not important. Okay, yeah. So we may have some small error, so that's not very important. Yeah. So we want our estimate very close. That's good enough. All right. So we choose the one right in the middle. After the first comparison, one of the two subarrays can be eliminated, right? So half of the data is gone, is eliminated. So not in our consideration anymore after one comparison. Okay, so let's look at the size reduction in this process. Yeah. So one of the two subarrays is dropping. Yeah. All right. Then in the remaining data, the next comparison, another comparison with the element, median element in the current array. Yeah, current array. So another subarray is drop it. Okay, one of the two subarrays. Drop it. Okay. Yeah. So the size of our current data is reduced by another half, and so on. Okay. So let's keep doing division, like this. Yeah. So at the end, we want to see after certain number of comparisons, we can stop. Termination. Yeah, we want to see. After certain number of comparisons, our process can terminate. Yeah. So that point is important. All right. So here, let's try to find some rule. Yeah. So after the first comparison, the size of our current data, n over 2. Yeah. N, the size of the original data. After two comparisons, our data size becomes n over 4, and so on. Okay? So after k comparisons, the data size of the current array, subarray, becomes n over 2 to the k. Yeah. So with this formula, now we want to study the termination point. For what k? So here, we use this k parameter to control the number of comparisons we need for the worst case. Yeah. So the question, can we estimate this k that corresponds to the worst case? Yeah. So that's our current objective. Yeah. All right. Yeah. So at what time should we stop splitting? Yeah. So here we need another criterion to tell us the stopping condition, to give us the stopping condition. Yeah. Because at this point we don't know it, right? We don't know what is the stopping condition. Yeah. So we need to study that. Yeah. After the last comparison, let's look at the data size. What is the data size after the last comparison? Yeah. So we need to create that criterion, right? We want to make that criterion for the stopping condition. Yeah. Can we say if the data size after last comparison is strictly less than 1, then we need no more split, right? Yeah. Because the data size strictly less than 1, then that subarray can contain at the most one element, right? Yeah. Yeah. Here, data size, we use a small line segment to represent that data size. Yeah. So the small line segment, the length of that small line segment is strictly less than 1. Then that interval cannot cover more than 2 elements, right? Here, let me draw diagram a little more, yeah, because I'm afraid it's too abstract for your understanding. If I just do talking, so it's probably too abstract. Okay, all right. Yeah. So here I still draw line segment represent the elements in this array. Yeah. All right. Yeah. So let me put many dots representing the elements in this array. Okay? All right. Then the distance between two adjacent dots, can we make it a 1? 1 unit. Okay? 1 unit of the length. Yeah. 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 So all of them. Okay? All right. Yeah. So the distance between two adjacent elements, it's 1, but think about it. If your data size, the length of certain, line segment, okay? So this size less than 1, can we say this subarray can only cover 1 element, at the most 1, right? So in that interval, you cannot cover more than 1 element. You can only cover at the most 1. If your subarray can only contain 1 element, can we say no more splitting? You don't need to do any further splitting, right? Yeah, because you only have 1 element. How can you do another round splitting, right? Yeah, no splitting anymore. Yeah. So here you can see this condition tells us no more round splitting. Yeah. Yeah. You can stop. You can stop without any problem. Yeah. Yeah. If the size is exactly 1, equals 1, then there is a possibility it can cover 2 elements, right? Yeah. Here, so we make it strictly less than 1. So you have no chance to cover more than 1 element. Yeah. So that's our way to determine the stopping condition. Yeah. So this is the criteria for stopping condition. Yeah. All right. Based on this understanding, now we can continue to do our analysis work. All right. Now, yeah. So let's look at this inequality. Yeah. So inequality. Yeah. So there were 2 inequalities here. Here. Okay. The first part, this part. Yeah. So that's our stopping condition, right? Yeah. So the current data size must be strictly less than 1. Yeah. All right. Then the second part of the inequality, this part. What's the meaning of this part? That means the size of the previous subarray. No, the previous subarray should be greater or equal to 1. So that means you need to do one more split, right? Yeah. So in the previous round, you cannot stop, okay? You still need to make sure there is no uncertainty for the splitting round, for the splitting situation, yeah? Because if the size is greater or equal to 1, there is still possibility the current subarray may contain more than one element, right? Yeah. So we don't want that to happen. Okay. So we need to do one more splitting. That means if you just do k-1 comparisons, you cannot stop. You need to do another round splitting to make sure the current data size is strictly less than 1, then you can stop. Okay? So you need 2 inequalities, not 1. Otherwise, think about it. If we do not add this part of inequality, what would happen? Then you can make that k as large as possible, right? Yeah. So you won't get the minimum number of comparisons for the worst case. Because our goal is we want to find a minimum number of comparisons for the worst case. Now, so this part, this right-hand side part, that inequality, help us to get a minimum number for k. Yeah. All right. That corresponds to the best solution. Yeah. All right. So let's try to, do some algebraic operation on this condition. Yeah. All right. Remove the common denominator. Yeah. Because we want to work on integers, right? Yeah. So these fractions not very friendly. Yeah. So we would like to work on integers. All right. Here, when we work on the integers, yeah. So this time, work on the integers here. Yeah. Yeah. Look at the inequality. Yeah. So one inequality is less and equal. The left-hand side part contains the equality case. But this right-hand side part, right part, does not contain equality. Yeah, does not contain equality. Yeah. Think about that. What does that mean? Yeah. All right. It does not contain equality case. Yeah. Can we improve? So here the question. Can we improve the right half of this inequality? Can we improve this? Yeah, because we have some room to improve it. How about that? Yeah, because n is strictly less than 2 to the k. N is strictly than 2 to the k. Yeah. Okay. Yeah. Can we say if n strictly? Can we say n plus 1 is less than equal to 2 to the k? Yeah. There is some room. There is a gap between those two numbers. There is a gap between n and the 2 to the k. These two integer expressions. There must be some gap, right? Yeah. That gap, at least 1, right? The smallest gap is 1. So that if we add 1 on n, it should be still less than or equal to 2 to the k, right? Yeah. In this case, we can add that equality in the right half of the inequality. Okay? That means we improve the inequality. Okay? We improve. We add 1. That's small improvement. Yeah. But we want to do the best we can, right? Yeah. So why you care about that small improvement? Yes, we care. Yeah. Yeah. Small improvement. Because we want to get the optimal solution. Think about that. For optimal solution, even 1 improvement, it matters, right? Yeah. 1 small improvement, it matters for the optimal solution. Otherwise, It may not be optimal, right? The solution may not be optimal. Yeah. All right, yeah, so here. Then, if we take log of base 2, yeah, so we can get rid of the power of 2 expression. Yeah, okay, all right. But, so here, yeah, because we have a way to improve this part of the inequality. Yeah, all right. Yeah, so let's look at here. So now we want to add the improvement part. Add improvement part here. Okay? Yeah. Yeah. For the optimal solution. Okay? Yeah. All right. So we want to derive the worst case formula for the optimal solution. Okay? Yeah. All right. Yeah. Yeah. Here, the improvement appears in this inequality place. Yeah. Equality, no room for improvement, right? Yeah. So for right half of the inequality, no room for improvement, yeah, because they could be equal. Yeah. But still, some little room for improvement. This side, okay, all right, yeah. So the improvement, we add a 1 on top of n, so we can make it, we can add equality case. That's improvement. So that's improvement. Okay? Then we take log base 2 on this improved inequality. This is improved version of inequality. Okay? Yeah. So after we add a 1, then we take log base 2, we get a better estimate. Better estimate. Okay? A small, tiny improvement, but we are targeting the optimal case. All right? So then you can see we take log base 2 this time. Yeah. So we have these 2 inequalities. Yeah. So because this part, so here we copy from the previous one. Previous one we already have that equality case. So no room for improvement. So we just copy it. Okay? But this side, there is some little room for improvement. So we change that n to n plus 1, and this time we have that equality case included. That's the best we can do. All right? Yeah. So this inequality is the best we can do when we target the optimal solution. The best we can do is this one. All right? Yeah. Then, the final conclusion. Now we are ready. After we get this inequality, we can make our final conclusion. The optimal solution for the worst case, for the binary search. All right? Yeah. Conclusion. In conclusion, we have 2 formulas. Yeah. Yeah. Because the upper bound formula and the lower bound formula. So there are 2 estimate formulas we can use for the worst case. All right. The first formula, this k sub max. Yeah, the max. Because worst case corresponds to maximum number of comparisons, right? Yeah. So that's the meaning. Yeah. Maximum number of comparisons for the worst case. Yeah. But we want to make this number as small as possible, corresponding to the optimal solution, right? Yeah. Optimal solution, as small as possible. Yeah. All right. Now, yeah. Here you can see, because the k number must be an integer, right? Must be an integer. So it cannot be a non-integer expression. So we use the floor function, ceiling function to make in upper bound, lower bound as integer expressions. Yeah. So for the lower bound, we take ceiling function. Yeah. Ceiling function. Okay? Yeah. No loss, right? When we make ceiling function on our lower bound, because we need to get the integer anyway, right? So when we do the ceiling function on our lower bound, there is no loss, right? Yeah, no loss. We know this k number must be an integer. So we take ceiling function moving up. moving up. So if it's a non-integer number, we're moving up. Still, it should be below k, right? Yeah, below k. Yeah. So we do not do any harm in this seeding function step. No harm. Okay? That's why our first formula will take seeding function of log base 2 of n plus 1. Yeah. So k, if we choose our k max to that formula, so that's a good choice. Yeah. All right. The first formula. Second formula, we use the upper bound this time. Upper bound, this time we need to use floor function. Now, we want to reduce this number as much as possible. So we are going down. Okay? So we do the rounding operation, rounding down operation. Okay? Floor function. Yeah. 1 plus floor function of log base 2 of n. Yeah. In this case, we do not lose any precision, right? Yeah. Same argument. We do not lose any precision. Data precision step. All right. So here you can see from the outside forms, we have two different formulas, right? Yeah. Which one is correct? Yeah. Based on the logic, both formulas have good chance to be our final formula. Both formulas have a good chance to be our final formula. Now, the candidates, two candidates for our final best formula. All right. Yeah. So then just quickly. Yeah. So the final answer, let me give you the final answer. Final answer is these two formulas are the same. We can prove mathematically, we can prove it mathematically, they are the same number all the time for any positive integer n. They're always the same. Yeah. So we can use mathematical induction to prove it. Mathematical induction. Okay? Yeah. So I talk about that. Fibonacci formula, right? Yeah. Mathematical induction. Yeah. We did that before. Here we can use mathematical induction to prove this formula always correct. Yeah. Then you can use either version, right? So yeah. Anytime, if I ask you similar questions, you just select one of the two formulas to use it. Okay, all right? Yeah, so here you can see, so the last thing here, the best case is 1, the worst case is this k max, okay? K sub max, yeah. So we have best case and we have worst case. Then the next question is how to calculate the average case. Yeah. So we leave it next time. Next time, we want to study this topic. How to find average case efficiency number for binary search. Yeah. So it's not that straightforward. We need to do quite some work to find the answer. All right? Yeah. That's it.